Hello, welcome to our group project, which is numerical method assignment, curve fitting using leaf data. So this is our group member, which is ERRA, me ASYIKIN, SYAHIRAH, and then UMMI LAILA.
Curve fitting is used to represent real-world shape and boundaries using mathematical equations. We choose BINTI leaf for this project due to its symmetrical shape and geometric structure. In this project, we use web plot digitalizer to extract the boundary coordinates and analyze them using Microsoft Excel to find the best fitting model.
Next, we're moving to data collection, which consists of 9 that begins by selecting a beta leaf because of its symmetrical shapes, smooth margins, and clear geometric boundary, make it suitable for mathematical analysis. For the second process, the leaf was glued onto a white sheet of paper to reduce background distortion, and a top-down photograph was taken as shown in the image. The image was then uploaded into Web Plot Digitizer. Using the 2D XY plots option, the axes were calibrated to convert pixel distance into coordinate value as shown in the picture. T coordinates points were plotted along the leaf boundary with 15 points on the upper side and 15 on the lower side. Additional points were placed in curved areas to capture the leaf shape more accurately as shown in the picture. The final process is where the coordinate data was exported as a CSV file and analyzed in the Microsoft Excel for future numerical calculation.
For the methodology part, the first step is computational framework and data processing. Microsoft Excel was used to store and process the coordinates. Then, to maintain the single value function, we split the leaf into two segments, which 15 points for the upper boundary and 15 points for the lower boundary. From the points, we then executed the regression model and mapped the specific data range. As we can see, the slide shows the analysis of data table in Excel, which smoothly maps out the specific data for our calculation. The second step of methodology is we evaluated 3 different mathematical models for upper and lower boundary. The models are linear least square fitting, discrete least square polynomial of degree 2, and discrete least square polynomial of degree 3. The 3 of them will produce a different general equation, as different normal equation in matrix will be used according to the degree. The last step of methodology is error analysis. To check the accuracy, we generated new y-value using our derived equation and compared them to the original data. After the visual comparison of y-old and y-nil using 2D scatter plot, we calculated the SSE by squaring the error formula, which is absolute y-new minus y-old. Then, the lowest SSE will represent the most accurate mathematical fit of the leaf. Now, let's take a look at curve fitting analysis, begin with linear least square fitting model. Here, we can see the linear function fx equal to a0 plus a1x. The 2 times 2 normal matrix form will be used that require the summation of x, x square, y, and xy. Our total sample size n is 30, which 15 for upper and 15 for lower. For upper leaf boundary, we substituted the data sum into the metric equation to solve for our constant a0 and a1. Then, we got our a0 is 9.1806 and a1 is 0.1197. This gave us an upper line equation of fx equal to 9.1806 plus 0.1197x. Then, we calculated the SSE and the total calculated for error sum is 40.9918. Next, we apply the exact same metric step to solve the constant for our lower leaf boundary dataset. And we will get our a0 is 3.6314 and a1 0.0153. This produces a lower line equation of fx equal to 3.6314 plus 0.0153x. From the sum of square error calculated, we have the total error sum of 32.2713.
Next, we move to the discrete least square polynomial of degree 2. As we can see, the polynomial functions for this fitting is fx equal to a0 plus a1x plus a2x squared. The 3 by 3 matrix form will be used to calculate and find the coefficients for a0, a1, and a2. Total number of points is 30, which is 15 for upper and 15 for lower boundaries. And degree m for this discrete least square polynomial is 2. So for the upper leaf boundary, this is the data that we find the summations of value of x, y until x squared y to use to find the coefficient. Here, we substitute the data summation from the previous table into the matrix form to find the coefficient and solve it by using simultaneous equation. And after that, we substitute into the least square function and we will get the fx equal to negative 2.6451 plus 5.4537x minus 0.5313x squared. After that, we find the sum of square error for this polynomial of degree 2 and we will get the error square is 10.7223. So for the lower leaf boundary, same as in the upper leaf boundary, that we need to find the summation value of x, y until x square y to use to find the coefficient. After that, we substitute the data summations from the previous table into the matrix form and solve it using simultaneous equations. We will get the A0, A1 and A2, and we substitute into the least square function. We will get fx equal to 8.5353 minus 3.0001x plus 0.3288x squared. Lastly, we find the summations of square error, and we will get the error square is 7.7561 for the lower leaf boundary.
Moving on to the next section, modeling the leaf profile using a discrete least squares polynomial of degree 3. To solve this, we use the function written and a 4 times 4 matrix from the normal equations across 30 total data. Starting with the upper leaf joins into a 4 times 4 matrix to solve the normal equations. This yielded the coefficients of A0 equals to 14.2590, A1 equals to negative 6.8215, A2 equals to 2.1181, and A3 equals to negative 0.1763. When evaluating the fit against our original data, the total sum of squared errors for this upper curve come out to 3.2239. Moving directly to the lower leaf boundary, we apply the exact same least squares framework to it. 15 in the second system of normal equations gave us a different polynomial. Coefficient of A0 equals to 9.4573, A1 equals to negative 3.8711, A2 equals to 0.5475, and lastly A3 we will get negative 0.0158. The final sum of squared errors for the lower boundaries is 7.6155. Together, these two cubic functions successfully map the entire leaf profile.
So now we're moving on to the result, which is the best fitting model for each section is the one that minimizes the total prediction error, known as the sum of square error SSE. So in this section, we will see three graphs, which is the linear least square fitting, the discrete least square polynomial of degree 2, and also degree 3. So first, we're going to look at the linear least square fitting of the upper leaf boundary graph. So as shown in the figure, for the left side, we have the observed upper boundary points of the beetle leaf, while on the right side, we have the presentation of the linear regression fit for visual comparison with the actual leaf shape. The maximum absolute residual of 3.1914 occurs at I equal to 9, indicating that the largest difference between the observed and predicted value near the leaf peaks and the sum of square errors, SSE, is 40.9918, showing that most predicted value closely match the observed point. So you can see the straight line, which is indicate the linear line. So now we're going to look at the result of the lower leaf boundary for the linear least square fitting. So on the left side, the graph will show that the boundary points of the beetle leaf that has been plotted, and also at the right side, you have the linear regression line overlaid to illustrate the fit against the actual leaf shape. So the maximum absolute residual of 2.9480 occurs at I equal to 7, indicate that the largest difference between observed and predicted value near the boundaries point. The sum of square error SSE is 32.2713, showing that most predicted points remain close to the actual data. The linear fit is successfully captured the overall trend of the lower boundary, though small deviations are noticeable at the extremes. This deviation reflects the limitation of modeling a curved surface with a straight line. As you can see, the straight line appears as the linear regression line. So now we move on to the discrete least square polynomial of degree 2, which is the upper leaf boundary. So as you can see from the linear, the shape of the line has been curved. So the line is the actually discrete least square polynomial of degree 2 for visual comparison with the actual leaf shape. The maximum residual of 1.7707 occurs at R equal to 8, indicating the largest difference between observed and predicted value near the leaf peaks. And the sum of square errors is 10.7223, showing that most points closely follow the fitted curve, as we can see in the result. So now we look at the lower leaf boundary for the polynomial degree 2. As you can see, it almost closely fitted the curve of the point of the leaf. The maximum residual of 1.9762 occurs at I equal to 7, indicating that the larger difference between the observed and predicted value, and the SSE is 7.7561, notably smaller than the upper boundary SSE, reflecting that the quadratic line fits the lower boundary more closely. Most predicted points align well with the observed data, showing minimal deviation across the boundary. Overall, the quadratic line captures the general curvature of the leaf boundary more accurately than a linear line before, though minor deviation remain at the peak and the edges. So now that you have seen the graph of the linear and also discrete of polynomial degree 2, now we're going to look at the discrete least square polynomial of degree 3. So this is the upper leaf boundary. As you can see, the line almost fit the actual point of the beetle leaf. The maximum residual of 1.220C occurs at R equal to 8, indicating that the largest difference between observed and predicted value near the leaf's peak. And the sum of square error is 3.2239, showing that most predicted points closely follow the fitted curve, as we can see in the graph. So lastly, this is the lower leaf boundary of polynomial of degree 3. So on the left side, you have the point of the y old and y new, and the right side is the actual of the curve fitting of the degree 3. So, the polynomial of degree 3 line overlaid for comparison with the actual leaf shape. The maximum residual of 1.9450 occurs at I equal to 7, indicating also the largest difference between observed and predicted value. And the sum of square error is 7.6155, slightly higher than the cubic upper boundary of SSE of 3.2239, reflecting that the greater the curvature of the lower boundary. Most predicted points align closely with the observed data, showing minimal deviation across the boundary. Overall, the cubic line captures the curvature of the leaf boundary more accurately than both the linear and quadratic fits, with only minor deviation near the peak and also edge.
So here we will discuss about the method and evaluations, upper and lower leaf boundary result, fitting accuracy and best model, and the last one is the discrete least square justification. So in this study, the discrete least square method was used to find the polynomial function that best represent the leaf boundary. The leaf was divided into two, which is the upper and lower leaf boundaries, and three models were tested, such as linear degree 1, quadratic, polynomial degree 2, and also cubic polynomial degree 3. The performance of each model was evaluated using the sum of square error or SSE. Since SSE measures the difference between the actual data and the fitted curve, a smaller SSE value indicates a better fitting accuracy. Therefore, the model with the lowest SSE was selected as the best model. So, for the upper leaf boundary, the linear least square fitting produced the highest SSE value of 40.9918, while the polynomial least square fitting degree 2 significantly reduced the error to 10.7223. The polynomial least square fitting degree 3 achieved the lowest SSE value of 3.2239, indicating the best fit for the upper boundary. Also, a similar pattern was observed for the lower leaf boundary. The linear least square fitting produced the highest SSE value of 32.2713, while the polynomial least square fitting degree 2 and 3 reduced the error to 7.7561 and 7.6155 respectively. Since the polynomial least square fitting degree 3 achieved the lowest SSE value, it was selected as the best model for the lower boundary. Therefore, the degree 3 polynomial model provides the most accurate representations of the leaf shapes for both upper and lower boundaries. So based on the SSE value we obtained, the fitting accuracy improved as the polynomial degree increased. The linear least square fitting produced the highest error, while the polynomial least square fitting degree 2 significantly reduced the error. And the last one, the least square fitting for polynomial degree 3 achieved the lowest SSE value because it has a greater flexibility to follow the curvature of the leaf boundary. Since the cubic polynomial produced the smallest SSE for both the upper and lower boundaries, it was selected as the best model for representing the leaf shape. Therefore, the cubic polynomial provides the most accurate approximations among the three models tested. So, as we can see that the discrete least square method was selected because the leaf boundary data consists of discrete coordinates points extracted using web plot digitized. Since the actual mathematical functions of the leaf boundary is unknown, it is not possible to determine the AZ equations directly. Therefore, the discrete least square method is used to find the polynomial functions that best fit the observed data. This method works by minimizing the sum of square errors, SSE, which measure the difference between the actual data points and the fitted curve. By minimizing this error, the method determines the most suitable polynomial coefficients and provides an accurate approximations of the leaf boundary. As a result, the discrete least square is an appropriate and reliable method for modeling the shape of the leaf.
In conclusion, this project successfully applied the numerical method of the discrete least square method learned in MAT575, which is Introduction to Numerical Analysis, to model the physical geometry of a symmetrical beetle leaf by capturing 30 discrete coordinate boundary points using web plot digitizer and processing them within Microsoft Excel. Linear degree 1, quadratic degree 2, and cubic degree 3 fitting function were successfully generated for both the upper and lower leaf boundaries. The model was tested with the sum of square error, and it was found that the higher degree polynomial terms provide the essential geometric flexibility required to capture natural curve. The poor performance of the linear fit could be attributed to the curve botanical pattern being modeled. Therefore, the polynomial of degree T proved to be the most stable and accurate mathematical representation for both leaf segments. This confirmed that the increasing the polynomial degree optimized boundary approximation and reduced data variation. Hence, the cubic polynomial function is selected as the best numerical model for successfully capturing and defining the organic shape of the beetle leaf in this study. Overall, this project demonstrates the practical relevance of numerical analysis technique in modeling real-world problems. The use of discrete least square fitting proved to be an effective and suitable approach for approximating shapes using sample data points. So that's all from us. Thank you.